Good morning, class. We are going to finish up section 1.2 today, and so we can move on when we pick up in class. So we are still in part 2, so this is on page 2 of the notes, and we are about half or 2/3 of the way down the page. We've been drawing these sketches of what different solutions would look like in water. So for this one, KOH, this is potassium hydroxide. So potassium hydroxide, when you put it in water, is going to dissociate 100%. So we have potassium, we have a hydroxide. We need to make sure that they are in the appropriate, the appropriate proportions. So for every 1 potassium, we have 1 hydroxide. So they should be in a 1-to-1 ratio. If we were to draw another potassium, another hydroxide would need to show up somewhere. The whole time there are water molecules interspersed throughout here, but for clarity, we are not actually going to draw them. So some explanation: potassium hydroxide is a strong base. And by strong base, it means that it dissociates 100%. It ionizes 100%. So every KOH that gets put into water is going to turn into a potassium ion and a hydroxide ion. There will not be any KOHs together in the solution. So if you were to put it in water, it would look like this. All of the KOH becoming potassium and hydroxide ions. Last one for the page is HF, hydrogen fluoride. Hydrogen fluoride, I'm going to go with the explanation first. HF is a weak acid. Let me scroll back a page, 2 pages actually, to HNO3. HNO3 was a strong acid, which meant it ionizes 100%. HNO3, all of it becomes H pluses and NO3 minuses. A weak acid only ionizes to a certain extent, not 100%. So ionization is somewhere less than 100%. And it depends on what compound you're talking about as to the actual ionization, but weak acid tells us it's definitely not 100%. So you would have some HF turning into H plus and fluoride ions, but a lot of these are going back the other way and turning into HF again. So you might have an H plus and a fluoride. Here they are in that 1-to-1 ratio, just like in the formula unit. But then here we've got an HF that did not ionize. Here's another HF, and here's another HF. So the majority of these in the weak acid are staying in the form where they are not dissociated. Only a few of them ionize. At the bottom of the page, asking what factors determine how well a substance dissolves in water. So a substance can dissolve well if, 1, it's a soluble salt, or a strong acid or base. or 2 if it is a polar molecular compound. These things will dissolve well in water. Remember, we had the silver chloride. It was an insoluble salt. It did not fall into these categories, so very little of it ionized, and we drew all of the AgCls on the bottom of the container. We had HF, the weak acid. Again, it didn't fall into these categories, so it doesn't dissolve very well. Factors determining how well a substance Factors that determine how well a substance conducts electricity. So things that ionize 100%. There would be lots of ions in the water that allow current to travel through them. That would be these things: your soluble salts, your strong acids, strong bases. Let's write this down. Strong acid, strong base. Strong acid, strong base. So if something doesn't ionize, so let's say dissolve well. Doesn't dissolve well. Scratch that. We're looking at conduct electricity. This is why we do everything in pencil in chemistry. Things that don't conduct electricity well, which are things that do not ionize well, or polar molecular compounds. Just like water does not conduct electricity well, pure water, it's a polar molecular compound. Adding more polar molecular compounds is not going to improve how well it conducts electricity. Really, what we need are ions. Ions are what conduct electricity in a solution. So in part 3, consider a solution that contains copper 2+, represented by the particulate diagram to the right. A sample solution was placed in a colorimeter at 635 nanometers, and an absorbance of 0.86 was reported. So on your notes, you should have a picture of a beaker here. It's got a solution, and there are something like that. So let's write this other data down. Absorbance is 0.86, and we're talking about a wavelength of 635 nanometers. This is the Greek letter lambda. It represents wavelength. Suppose water was added so the volume of the solution doubled. So let's duplicate this page a couple times. Okay, so here's our new beaker, and we're doubling the volume of the water. So first off, the question is, so sketch the particulate diagram. Here's the water level. Here's our copper. Here's a copper. Here's a copper, and here's a copper. So now we have to ask what changed. Did the moles of copper change? So did we actually add any copper? No. Did we take any copper away? No. So the moles of copper stayed the same. So what changed? We added water. So the volume of solution changed. What else changed? When you add water, but the number of moles didn't change, you have also changed the concentration. Remember this, concentration and molarity is moles per liter. So what we did was increase this number. So the moles stayed the same. We increased the volume. When you make this bottom number of a fraction larger, this number is going to change. So volume went up, concentration went down. Both of these things changed. Moles did not. If a sample of this new solution was placed in a cuvette and run through a colorimeter, what would be its expected absorbance? So here's what we had. Originally, we had a certain concentration with an absorbance of 0.86. If we cut the concentration in half, let's see what's going to go on here. So A equals A times B times C. A is a constant, it's not going to change. B is a constant, it's not going to change. So we basically have A is somehow proportional to C. Maybe we could rewrite it like that. A is somehow proportional to C. So if we had 1/2 the concentration, we would expect 1/2 of the absorbance. So we could expect an absorbance for this solution of 0.43. B, suppose half the volume of the original solution was spilled. So here's our original solution, and we spilled half of it. Sketch a particulate diagram for the resulting solution. So here it is. There's half the volume. And if you spill half the water, then presumably you have also spilled half of the copper. So here's a copper ion. Here's a copper ion. So let's look at what changed. Well, from here to here, over here we have 4 coppers, here we have 2. So the moles of the copper ions have changed. What else has changed? The volume went down. The volume changed. What else changed? So remember, let's look at molarity is moles over liters. So here's what happened. What is the concentration when you have half the number of moles and half the volume? 1/2 over 1/2 cancels, and concentration stayed the same. The concentration did not change. This molarity is more about a ratio than about how much solution is there or how many moles are there. These two are related in the ratio that makes this. What is the absorbance of this solution? The original solution had an absorbance of 0.86. This one, we determined that the concentration stayed the same. The only thing that changed was the volume and the actual number of moles. Concentration didn't change. Which means our absorbance is still 0.86. Imagine this, you made 10 milliliters of a blue solution the other day. You pulled out 1 milliliter, it had a certain absorbance. If you were able to test more, it should have the same absorbance as long as the path length didn't change. If you used a smaller path length, you would have to change some factors. But the absorbance itself didn't change based on did I start with 1 liter or a half liter or anything else. Part C. Suppose half of the volume of the original solution was evaporated. So here's this. We have 4 coppers at a certain amount of solution. And now we come over here, half of the volume evaporated, which means that the water evaporated, but the copper does not evaporate. So what changed here? Did the number of moles of copper change? No, it stayed the same. We have it represented as 4 over here and 4 in the new situation. The volume of the solution changed. It decreased by half because the water was escaping and evaporated. So let's take a look at concentration. Did concentration change? Here we have molarity equals moles per liter. That's typical. And over here we have the same number of moles, but we have a much smaller volume. Maybe we could write it a little better as 1/2 the volume. So what you end up with is twice the concentration. Concentration increased. If we put this in a colorimeter and on the assumption that it worked without any hiccups, what would the absorbance be? So the absorbance of this solution is 0.86. The absorbance or the concentration of this one is twice as much. So remember A and B are constants, here's C. So what is the absorbance when we double the concentration? Should be this. And so our new absorbance should be 1.72. Now, if you read the lab closely, this is probably beyond the acceptable limits for absorbance, but strictly from a numbers perspective, this is what you could expect based on the calculations. So a quick recap on the things that are important in this unit. We talked about Beer's law. This formula is on your AP formula sheet, and it defines all 4 of these quantities. A is the absorbance. That's your number that you would expect to see based on the colorimeter. A is the molar absorptivity constant. It is a constant for a specific substance. B is the path length. It's pretty much always 1 centimeter. And C is concentration. We looked at an absorbance versus wavelength graph. And so they range from about 400 to 800, 600, 700, something like this. And let's see. something like this, and the numbers really could go on. This graph, the absorbance versus wavelength graph, will give us an idea of what wavelength is best for our experiment. So we've been using the same basic graph like this for the whole time. We've been working with blue solutions. But let's say that we have a different graph and it looks something like this. Now the goal here is to figure out the best wavelength. And to figure out the best wavelength, what we need to do is look for the highest peak and then draw it down. And we would say the optimal wavelength for this experiment is somewhere, here's 500, here's 550, maybe 525 nanometers, maybe 530, somewhere in this range. Then we had our absorption versus concentration. And in general, the data points starting at 0, 0 should follow a fairly straight line. So we'll call this an absorption of 1, 0.5. Something like this. And concentration is increasing, let's say, something like this. So, if you read your lab carefully or if you pay attention in class, you probably remember that absorption, or the A, is only really acceptable for data points between 1.0 and 0.2. Under here, it's probably not quite accurate, and above 1.0, it's probably also not accurate. What we would expect is a line that continues linearly, but what we find in the real world looks something like this. It starts to kind of track downwards like this and eventually level off.